Hello, today I want to look at what is called Bells Inequality. John Stuart Bell, 1964, was responsible for this. It is a response to the Einstein-Podolsky-Rosen paradox, about which I produced a video recently. Now, just to review what that paradox said, what Einstein and Podolsky and Rosen argued, that if you have some kind of system like energy or a nuclear reaction, whatever it may be, that is responsible for pair production, you might produce, say, an electron and a positron. But what you find by experiment is that if you measure the electron spin, say, against the z-axis, the vertical axis, and you find that the spin is upwards, you might not, you might find it's downwards, but if you find it's upwards, then what you will always find is that the positron spin will be down. In other words, those two spins will always be exactly opposite. Similarly, if you measure the spin along the, say, x-axis, and you find it's in that direction, then were you to measure the spin along the x-axis of the positron, it would always be in the opposite direction. Now, Heisenberg's uncertainty principle says that you cannot know simultaneously both the spin in the z direction and the spin in the x direction. But this appears to suggest that you can, because what could happen is, here is an observer Alice and here is an observer Bob. And what you can say is that when this electron-positron pair is emitted, Alice will measure the spin in the z direction and find, let's say, that it's vertical. She then shouts across to Bob, I have found a spin in the z direction that is up. If you were to measure your spin, we know that you would find that it's down. But don't do that. Instead, measure your spin in the x direction. And so Bob is supposed to measure a spin in the x direction and find that it's, say, to the right. He would then know that his z direction spin was down and his x direction spin was to the right. He would know both values at the same time, but Heisenberg says he can't. So in practice what would happen is, if Alice measures the spin in the z direction of this electron, Bob cannot measure the spin in the x direction of the positron. But if Alice doesn't make that measurement, then Bob can make the measurement in the x direction. And the puzzle, the paradox is, how does one particle, how does this positron know whether or not Alice has made a measurement here? And we said that there were two possible explanations. One is that the electron and the positron are in constant and immediate communication. No matter how far they fly apart, no matter how far apart they are communicating to one another in an entangled state, instantaneously, what is going on. But of course there's a problem with that. That would suggest that information is being passed instantaneously that is faster than the speed of light. And special relativity says that's not possible. That's what's called a violation of locality. The second explanation is that when these two particles were first produced, when they were born if you like, they were each embedded with a kind of DNA or hidden variables that would forever govern precisely what they would do in the entirety of their life. And those hidden variables would ensure that they would always remain entangled, because that DNA would always govern what they behaved in doing. Now, since it was thought that locality couldn't be violated, in other words, you couldn't have constant communication of an immediate nature because that would violate special relativity, Einstein, Podolsky and Rosen thought there must be hidden variables embedded in these particles that would dictate what they did. And it was Bell's inequality that shows that there can't be those hidden variables. Now, to understand how Bell's inequality works, let's first look at a very simple example. We're considering children playing in a playground. Some of them are wearing hats, Some of them are wearing scarves and some of them are wearing gloves. It's a cold day. All of them are at least wearing one of those items of clothing. Some are wearing two, some are wearing all three. And we can represent those children by overlapping circles. They're sometimes called sets. This is set A. This is all the children wearing hats. This is set B, all the children wearing scarves. And this is set C, all the children wearing gloves. Now where A and B overlap, that's this area here, that means the children are wearing hats and scarves. Where A and C overlap, that's this area here, the children are wearing hats and gloves. Where B and C overlap, that's this area here, that means the children are wearing scarves and gloves. And right in the middle where A, B and C all overlap, that means those children are wearing hats, gloves and scarves. And what Bells Inequality says is that all the people who are wearing hats but not scarves, plus all the people who are wearing scarves but not gloves, is always greater or equal to all the people who are wearing hats but not gloves. And I'll prove that simply by numbering each of the regions. 1, 2, 3, 4, 5, 6, 7. So if you say A not B, well, A not B is region 1 plus region 4. 2 and 5 are part of B. So 1 plus 4 is A not B. What is B not C? Well, B not C is going to be 3 plus 2 because 5 and 6 are part of C. So this is plus 3 plus 2. And that, says Bell, has got to be greater than or equal to A not C. Well, A not C is 1 plus 2 because 4 and 5 are part of C. So now we have that 1 plus 4 plus 3 plus 2 must be greater than 1 plus 2. And that's obviously true because we've already got 1 plus 2 on this side. Let's put the 1 plus 2 there. Plus 4 plus 3 is greater than or equal to 1 plus 2. Well, it will be equal to if there are no children in categories 4 or 3. But if there are any children in categories 4 or 3, what is 4? 4 is that they are wearing hats and gloves but not scarves. 3 is that they are wearing scarves but not hats or gloves. If there's anybody in that, then this equality, or rather inequality, will be true. Incidentally, at this point I acknowledge Professor Leonard Susskind, who does something very similar to this in his videos on quantum entanglement. Now, how does this help? Well, we need to think about, for example, light. Let's take light which can be unpolarized. That is to say, the electric and magnetic fields can be oscillating in any direction. You can pass that light through what's called a polarizer. And a polarizer will polarize the light in one direction only. Let's suppose that the polarizer will polarize the light in the up direction, up-down direction. So the light passes through the polarizer and comes out the other side, and it is polarized in the up direction. Well, now let's suppose we take light that's unpolarized, pass it through an up direction polarizer, it comes out the other side polarized. Now we pass it through a polarizer that is exactly at 90 degrees to the vertical polarizer. What will happen? The answer is nothing comes out the other side. But if we took the same unpolarized light, passed it through a polarizer in the vertical direction, and then passed it through a polarizer at the 45-degree angle, some light would come out. Not as much, but some would. And if we then pass that through the polarizer that was, as it were, horizontally polarized, again, some light would come out. Not as much, but some would. So some light gets stopped as you go through this polarizer, more light gets stopped as you go through that polarizer, and more light again gets stopped as you go through that polarizer. But the point is that having gone through a vertical and a horizontal polarizer, you still have some light left because you had this polarizer that was at an angle in the middle. Whereas if you'd done it this way, nothing would go through. Well, that's an experiment. You can do that and you can demonstrate it. But now let's look at that from the point of view of an individual photon. Here is a photon that could be polarized in any direction. In practice, of course, it's only going to be polarized in one direction. We just don't know what it is. And as it comes to the polarizer, it either will or it won't get through. So it might be part of the photons that get stopped, and it might be part of the photons that get through. Similarly here, a photon comes along. If it gets through this polarizer, that's fine. It's polarized in the vertical direction, but it then definitely won't get through that polarizer. But here's the odd thing. Here comes our self-same photon. It gets through this polarizer and is polarized in the vertical direction. It then gets through, or it may not, there's a probability it will or it won't. It gets through this polarizer, it's then polarized in the angled 45-degree direction. And then when it gets to this polarizer, it might get through or it might not. And if it does, it will be polarized in the horizontal direction. And whether or not it gets through those polarizers is a quantum mechanical phenomena. You cannot predict which of those photons will get through. Some do, and some don't. So now let's try an experiment. And this is an experiment of entanglement. Again, we're going to have some process that produces pair production. In this case, I'm going to produce two photons. And they shoot off in opposite directions into the laboratory of Alice and Bob, who are going to have polarizers. And they're going to have just three types of polarizer. One is the polarizer that is vertical, one that is a polarizer at 120 degrees, and one that's a polarizer at 240 degrees. Now it's important to notice that you cannot predict what the polarization of these two photons will be. It could be in any direction, but if it's pair production, they will be the same. So if you produce two photons, they will have the same polarization. If you then produce another two photons, they will have the same polarization, but not the same as the earlier two, if you see what I mean. So what we're going to do in this experiment is we're going to constantly produce pairs of photons. What we know is that each pair will have the same polarization, but the next pair will have a different polarization. And what we're going to do each time we produce a pair is that Alice and Bob are going to randomly select, they've each got these three polarizers, and they're going to randomly select one of them and see if that photon goes through the polarizer or not. Now, according to the Einstein-Podolsky and Rosen paradox, these photons are supposed to contain hidden variables. That is, information that will tell them how to behave whatever circumstances they face. So presumably they must contain information that will tell them whether or not, for certainty, they will go through these polarizers. Because Einstein didn't like the idea of it all being probabilistic. He wanted there to be certainty in all of this. He once said, "I like to think that the moon is there even when I'm not looking at it." There's nothing probabilistic about this. He says, we must know, somebody must know, the photon must know whether it's going to go through these polarizers or not, and that's a hidden variable. So one of the hidden variables will be, will you go through polarizer 1, will you go through polarizer 2, and will you go through polarizer 3? And if hidden variables exist, then although we don't know what they are because we haven't discovered them yet, then they must absolutely determine how a photon will behave if it meets one of those polarizers. And we find that there are 8 combinations of this information. We can say that the first combination is, if we take, for example, the 3 polarizers, 1, 2 and 3, we can say that the hidden information may say you can go through all 3. The second option is the hidden information says you can go through 1 and 2 but not 3. The third option is you can go through 1 and 3 but not 2. The fourth possibility is you can go through 1 but not 2 or 3. The fifth possibility is that you can't go through 1 but you can go through 2 and 3. The sixth possibility is that you can't go through 1 or 3 but you can go through 2. The seventh possibility is that you can't go through 1 or 2 but you can go through 3. And the eighth possibility is you can't go through any of them. And those are the only bits of hidden information that could be contained in relation to whether or not those photons will go through any of those 3 polarizers if they happen to encounter them. And don't forget what we said was that every time you do a pair production, you will get a different bit of hidden information. So it won't be the same each time. The first pair production might have this. The second pair production might have this. The third might have this. You don't know. But what you do know is that each of those photons will have the same of those variations because they will both contain the same hidden variables. Now let's look at the experiment which Alice and Bob do. They are each randomly going to pick up one of their polarizers and see if their photon will go through it. So the combination could be that A and B, or B and C, or A and C. Now what will happen for each of these 8 variations? Remember, we don't know which hidden information photon we've got. All we can do is do the experiment. Well, what we want to ask ourselves is, when does Alice and Bob get the same information, the same outcome with their photon, and when does it differ? Well, if one has an A and one has a B polarizer, then in each case the photon will go through because its hidden information says it will go through. Sorry, it should be not an A and a B. It should be a 1 and a 2 and a 3, or a 1 and a 3 polarizer. We know that in this, if the photons have this hidden information, they're going to go through 1 and 2, so they'll be the same. They'll go through 2 and 3, so those will be the same. And they'll go through 1 and 3, so those will be the same. This is not very well written, is it? That's 1 and 2. This is 2 and 3. This is 1 and 3. It's the combinations of the polarizers that Alice and Bob have used for the particular pair production that I'm just going to interrupt myself at this point because, having looked at the video, I think I haven't explained it quite as clearly as I would wish. So I'm going to do a kind of an explanation within an explanation and go through a little slower. What we are saying is that we're going to have pair production of photons. Some process is going to generate 2 photons, and those photons will move off in opposite directions into the laboratory of Alice and Bob, who can perform measurements on them. And what we have determined experimentally is that although we don't know what the characteristics of the 2 photons will be in terms of their polarization, they will both have the same polarization. If we do the experiment again, we will generate another 2 photons. Those 2 photons will have the same polarization as each other, but not necessarily the same polarization as the earlier pair. Now what I've said is that each of them has 3 polarizers. A polarizer that will let a photon through in the vertical direction, in the 120 degree direction, and in the 240-degree direction. And Alice and Bob are going to randomly select from their polarizers, put them in front of the photon, and they're going to see if the photon goes through or if it doesn't go through. Those are the only two options. They can see it go through or it doesn't go through. Of course, there may be occasions where they both pick up the same polarizer. Now, there's no experiment in that at all. We know that if you pick up the same polarizer, the photons will either go through both or go through neither, because they're both polarized in exactly the same way. So if they go through if this one will go through a vertical polarizer, so will this one. So any time that Alice and Bob choose the same orientation of polarizer, we can ignore that experimental result because that's bound to be the case. We already know that's the case. It's only when Alice and Bob pick up different polarizers that you get information. And what we want to record for each experiment, every time we do a pair production, we're going to do this experiment where Alice and Bob randomly select from their three polarizers and see whether the photon goes through. The question we want to ask is, do they get the same result or a different result? Now, a same result means that the photon goes through both polarizers, or the photon goes through neither polarizer. A same result is they both go through or neither go through. A different result means that a photon will go through one polarizer but not the other one. I hope that makes what follows a little easier to understand. So now let's look at this one. If you have polarizers 1 and 2, then you'll get the same outcome. If you have 2 and 3, you'll get a different outcome because the photon will go through 2, but the photon won't go through 3. Similarly for 1 and, this is 1 and 3, let's scrub that out, 1 and 3. For 1 and 3, you'll get different. If you come down here, for 1 and 2, you get different. From 2 and 3, you get different. 1 and 3, you get the same. Here, 1 and 2, you get different. 2 and 3, you get the same outcome. 1 and 3, you get different. 1 and 2, different. 2 and 3, the same. 1 and 3, different. 1 and 2, different. 2 and 3, different. 1 and 3, the same. 1 and 2, the same. 2 and 3, different. 1 and 3, different. And this one, 1 and 2, the same. 2 and 3, the same. 1 and 3, the same. Here the same will be that the photon doesn't go through any of them. So it won't go through 1 and it won't go through 2. That's the same. So what have we seen here? That in these two positions, the photon will definitely go through both polarizers, whatever polarizers you happen to choose. In these examples, you have a probability of 1/3 that the photon will go through the combination of polarizers that are chosen. And the point of that long-winded explanation is that you would expect that if you did that experiment where you have pair production of photons and then Alice and Bob randomly select from these polarizers and hold them up in front of the photon and check whether the photon goes through or not, since you don't know which hidden variables those photons will have, you can at least say that you would expect that on 1/3 of occasions you would expect the outcomes to be the same. So if you did the experiment 100 times, then 33 times at least the experiment would come out to be the same. And that's basically Bells inequality. Bells inequality in this particular case says that you get the same outcome greater or equal to 1/3 of the times you do the experiment. By the same logic as we used for hats, gloves and scarves. The only trouble is that when you do the experiment, you find that you get the same outcome greater than 1/4, 0.25. And that means that 0.25 has to be greater than or equal to 1/3, which it clearly isn't. And so Bells Inequality shows us that this analysis of hidden variables can't be true. There can't be hidden variables, because if there were absolutely determined variables that said whether or not the photon would go through the polarizer, you would expect that at least in 1/3 of occasions you get the outcome of the same measurements, whereas experimentally you only get that on 1/4 of occasions, and 1/4 is not greater than or equal to 1/3. And so that appears to rule out the possibility of hidden variables. So what does it leave? Well, it leaves, since we said there were 2 possibilities, one was that the photons were communicating with one another instantaneously, and the other is that they had embedded DNA. If we rule out the idea that they have embedded DNA or hidden variables, we are left with the only other conclusion, which is that somehow these 2 particles are in constant communication instantaneously, thus violating the principle of special relativity and what is called the principle of locality. Now, whether that is true or whether this can all be explained by another as yet unthought of explanation has yet to be discovered. The electron pair is emitted. Alice will measure the spin in the Z direction and find, let's say, that it's vertical. She then shouts across to Bob, "I have found a spin in the Z direction that is up. If you were to measure your spin, we know that you would find that it's down. But don't do that. Instead, measure your spin in the X direction." And so Bob is supposed to measure a spin in the X direction and find that it's, say, to the right. He would then know that his Z direction spin was down and his X direction spin was to the right. He would know both values at the same time, but Heisenberg says he can't. So in practice what would happen is, if Alice measures the spin in the Z direction of this electron, Bob cannot measure the spin in the X direction of the positron. But if Alice doesn't make that measurement, then Bob can make the measurement in the X direction. Responsible for pair production, you might produce, say, an electron and a positron. But what you find by experiment is that if you measure the electron spin, say, against the Z-axis, the vertical axis, and you find that the spin is upwards, you might not, you might find it's downwards, but if you find it's upwards, then what you will always find is that the positron spin will be down. In other words, those 2 spins will always be exactly opposite. Similarly, if you measure the spin along the, say, x-axis, and you find it's in that direction, then were you to measure the spin along the x-axis of the positron, it would always be in the opposite direction. Now, Heisenberg's uncertainty principle says that you cannot know simultaneously both the spin in the z direction and the spin in the x direction. But this appears to suggest that you can, because what could happen is, here is an observer Alice and here is an observer Bob. And what you can say is that when this electron positron... Hello, today I want to look at what is called Bells Inequality. John Stuart Bell, 1964, was responsible for this. It is a response to the Einstein-Podolsky-Rosen paradox, about which I produced a video recently. Now, just to review what that paradox said, what Einstein and Podolsky and Rosen argued, that if you have some kind of system, like energy or a nuclear reaction, whatever it may be, that is